recurrence relation. In order to analyze the efficiency of the merge sort, we need to do math operation. So the first thing we need to do, derive recurrence relation. And when we do it, we want to estimate the worst case efficiency. Okay? So not the best case, not the average case, the worst case efficiency. Yeah. All right. So let's look at this given array. Okay. We use this t function, t of n, the running time, the time function, running time function, and here we use it to represent the number of comparisons. Yeah, we know equivalent, right? So t of n we can use represent number of comparisons we need for the merge sort. All right. Then we make even split based on our algorithm. Yeah. The first subarray, the second subarray. So the size approximately even. All right. Then conquer. So divide, then conquer. To conquer the first subarray, we need to pay this much cost. That's the cost we need to pay. To conquer the second subarray, we need to pay this much cost. Okay? Yes. Sorry. Yeah. It's my microphone. So I don't know if it's good or not. All right. Then there is a merge step. Okay? The merge step, remember, based on our analysis of part 2, we need to pay this much cost. Okay? Yeah, this much cost. Yeah. Put things together so we can get a equivalence relation. Yeah. So very simple, straightforward. Yeah. All right. This is our equivalence relation. The base case, size 1, no comparison. Size 2, 1 comparison. Okay? So then equation like this. So we need to solve this recurrence relation. Okay? Yeah. How to solve it? Consider a simpler case. This strategy, we try to make our life easier. So we don't do that, our adversaries thing, make our life harder. We make ourselves easier. Okay? So here we choose n equals power of 2, 2 to the kth power. Okay? So then our recurrence relation becomes this version, because this time when you do division by 2, you get a nice formula. Okay? 2 to the k minus 1. No fraction, so we don't want to see fraction. Yeah, so that's what we want. Yeah. So we get that. The question is, what's the next step? What is the next step? See? Yeah. If we try to use our experience before, it may not be easy. Remember, when we do things before, we subtract something, right? Remember, we subtract something. Yeah? Probably you can still try that way. We want to subtract certain number. Okay? But can you figure out that number? You can try. You can try. So based on my intuition, it should work, subtract certain number. But here I want to introduce you a new method, not subtraction method. I call it division method. Okay? So it's a new method. We do the transformation using the division method. What division do we do? So this time we divided by 2 to the kth power, both sides. Why we do that? Same idea as before. If we do that, we can explore similar structures at the two sides of the recurrence equation. They have the similar structure. Yes, they are. So we can use this information to do what? To make the solution easier. All right, so let me go to the next step. All right, so we start from this equation. Let's introduce, so with a similar structure, let's introduce new function. Okay, so the function to get a better view. Okay. All right. Let g function equals this one. G function, okay. Yeah. Now we simplify, so the k minus 1, that expression. So we simplify our original recurrence relation in this way. Is this much easier to solve? Right? Yeah, much easier. So we can solve it easily. Yeah. The final solution. Now we are ready to get a final solution. Okay? Yeah. So let's do several times, right? And we can find invariant. The size number plus the constant number, it's a constant k. It's fixed, invariant. Okay? So the last one, g of 1 plus k minus 1. G of 1, it is 1 over 2. So why g of 1? Yeah. So you may ask me, some of you may ask me, why g of 1 equals 1 half? Based on the definition, g of 1 is 2 to the first over 2, right? T of 2 equals 1, so that's why 1 over 2. Okay, so plug in, so we get g of k equals k minus 1 half. Okay, yeah. So let's go back to the original expression. G of k equals this fractional expression. So we write this way. After simplification, we know n equals 2 to the kth power. After simplification, you can see we can represent k as log 2, log base 2, log 2, log base 2 of n, log base 2 of n, So then t of n approximately n log n. How about that? That's what we want to get. That is our goal, big theta of n log n. Here the base is not important. We know that. Okay? The base number is not that important. But we achieve our goal through this analysis. Okay? Yeah. So we complete this merge sort, the whole procedure and analysis. All right. So that's the end of this video. But I still have quite some time left. So I look at, still 10-something minutes, even 20 minutes. So I can still record another video. So waiting for my video number 4. All right, but I may need some time to prepare that video. All right, that's it for this one. But there is another one left.